Hello and welcome to another Solana tutorial. Today we're gonna talk about Program Derived Addresses, PDAs. That's a very interesting concept in Solana, and if you ever want to develop smart contracts, that's definitely a concept that you should know about. So let's get started. Because that's what the 1.69k people are here for, to learn about Solana. Yes. Let's get started with a little bit of theory and our favorite program to illustrate stuff, Paint. Yeah. Okay. Let's try this. This will be horrible, but I'm gonna try anyway. Let's make it a bit bigger. Maybe that helps. Okay, maybe some super basics. Your private key, or let's call it the secret key, can derive a public key. So if you have the private key, you can make some mathematical operations to get the public key. So for instance, my secret key, JSON, I create a new key pair. Let's make this a bit bigger. Oh, fuck my shoulder. Then this here is my private key. So that's just the integer values that represent my private key or secret key. And from this secret key, I can derive the public key by calling Solana address and providing this key pair. Then it will calculate the public key from it. Same way that you can calculate the private key from the seed phrase. So your seed phrase can derive the secret key, but not the other way around. So from the private key, you cannot get the seed phrase, or from the public key, you cannot get the private key. So far, so good. The way this is done, the public key derived from the secret key, it works over elliptic curve cryptography. So ED, if you want to know exactly, you can read it in the white paper. It's called ECDSA. And I'm not an expert on this, right? I'm not a cryptographer. Elliptic curve digital signature algorithm, where you basically provide an elliptic curve, a base point, and then you can select the private key and calculate through the elliptic curve the public key. And the specific elliptic curve that is used for that, I think is called EC225 something. There, the 25519, which provides 128 bits of security. So that's the private key size, and the public key is the same size, so it's twice that. Yeah, and the curve looks something like that, with a base point that is something with primes because security. I don't know. I'm not a security expert. You can read up on that if you're really interested. And that's, I guess that's too mathematical. I don't even want to get into that. Point is, there is a curve that we use to derive the public keys from private keys. And to make things simple for our monkey brains, so that's not reality, but that's my graph. See, that's why we use Paint. We have some kind of curve. I don't know. I'm just gonna draw a random curve in here. Let's say that's our curve that we use, and let's say the X's down here, those are my secret keys, and on the plane there are my public keys. So for any given secret key, let's say here, this is my secret key, I can then derive that here. That's my corresponding private key for that given secret key. Conceptually. That's not how that's just conceptually. And for any point on this, for any given private key, I can find out the public key. Now the curve is not on the entire public key space. So there is a public key, for instance, this one here, that does not lie on the curve, which means that for this public key here, there is no private key. There is no secret key that can derive this, since it's not on the curve. The secret key down here, in my stupid example, would derive this key on the curve. Again, it's just a stupid example. So there are public keys that are not on the curve, is my point. And we use those as our PDAs. So maybe we should go a step back and first have a look. What is a program derived address and why the hell do we need that? So for this, there is no secret key to derive this public key. But what is it derived from then? For our program derived address, we use, first of all, the program ID plus some kind of seed. Some seed phrase similar to this seed phrase but different. Why am I even trying to explain this? And the seed phrase essentially is just some bytes. Usually from a string you get the bytes and then you use that as a seed phrase. We'll have a look at that when we actually implement it in a second. So with the program ID and the seed, we will then derive a new public key. The program ID, let's have a look at my program that I wrote. You know, that's going to be this. That's the address where the program lives for fee, redeem, counter, that was that. And then the seed phrase can be anything, and any bytes. Oh fuck, you don't even see this. I'm completely in the way. Hold on. Let me move here. Okay, maybe that's better. My video making skills, oh man. So from the program ID and any seed, I can derive a public key. Okay. Now, this public key can lie anywhere on the public key address space, but we might be unlucky and we might just pick a point that is on the curve where there would be a private key for it. And the chances for that are actually 50-50, not as drawn in this example, but it's like 50-50 that you get a point that is actually on the curve, which means there exists a secret key that could derive this public key. And that's not what we want. So we will also add a bump seed to that, which is just another byte starting with 255. And if then the resulting public key is on the curve, then we go with 254. And then we check, is the derived public key now on the curve still? And then we go with 253 and with 252 until we find a public key that is not on the curve, such as this, where there is no secret key that can derive it, but we can derive it with our program ID, our seed, and the bump seed. Now that's a lot of theory. Why the hell do we even need this? We need this because we might want our program to be able to sign for some things. Because when you sign a transaction, you need to have the secret key or a private key to prove that you own the associated address. So with the private key, you can sign a transaction. Obviously, for a program to hold the private key is not ideal because the program lives on chain and everybody can look on chain. So storing the private key on chain is just not a good solution because then everybody can just steal the private key. That's why we need those program derived addresses. Because with those, the program can say, hey, it is me, I am this program, and I know the seed and bump seed, and thereby I can prove that this public key is mine and I'm allowed to sign for it. Does that make sense? So PDAs essentially are a program's way to sign. When do you need this? Well, simplest example, you have like a treasury of Sol or any token, and you want to send some tokens from that treasury to another address. The program can approve this by signing with the seed and the bump seed and CPI, the system program. So use a cross-program invocation, I think is what you call that, to tell the system program to transfer the Sol, or to tell the token program to transfer some tokens. That's what we use PDAs for. Also, we can use PDAs just as a nicer way of handling our addresses, because this seed can be anything, and it can also be depending on some other input. Like you can put another account as the seed, for instance. You can say, I have my program ID plus some seed phrase, and part of that seed phrase is also another customer public key, and then my bump to get another address. And then this is different for every user. So every user will have their own account, but we can already find out where that account will live. So we can calculate this public key already before we use it. We don't need to create a new key pair and then pass that into the program and then remember the public key that we passed in. We can always just use the same seed to derive it. For our fee redeemer program, if we have a look how we did that here, we provided the public key of the account key pair and had to sign as this as well, that we actually own this, to initialize. And in our actual program, in the initialize, we just used this account. We could use a PDA for that instead and derive the account address in here in the program. And then we can do the same here. Then we don't need to always pass in this account. Although we need to write to this account, so we need to have it in the accounts anyway here. We will not get around doing this because we want to write on it. But we can also always derive it on the client side as well with the find program account. All right, I would say we do a quick little example. I'm gonna jump back here. That's the theory session done. Let's write an actual program. Do we want to change this or do we create a new program? I'd say let's create a new one and do the example with the treasury. Let's do that. PDA tutorial anchor init. Yeah. So what is our goal? We want to create a quick little program that just allows us to send and receive funds. And the program we only need for the receiving, because sending funds to a treasury, we can do that anytime. We don't need a signature for that. Okay. So PDA treasure. Let's get this party started. What do we need to do? We need to find out our program address. It's our key pair. Do we want a different one? Just need to bring that in here. We need to make a function that allows us to withdraw. Let's make a function that allows us to deposit as well. We will do a deposit, withdraw. And for all of that, we need no accounts. Okay. Oh, we will need the system program, not no accounts. Right, so let's find out how we actually transfer funds with the system program. Okay, I think it's easier to find a program that actually just does it and then we read from there. So GemWorks. Look, there we have it with the seeds and everything. So it takes that as the seed and then the farm key treasury and then the farm ID. That's the entire seed plus the pump seed plus the program itself. Then you can derive this account. There, system instruction, transfer from the treasury to the destination. And here the signer, again, you have the byte, then this, and then the bump. You know what? Instead of deposit, let's just print. Let's start with a print funds, where we just print how much sol is on the address. How do we actually get a PDA? There is a thing called find program addresses that we can call, but I also don't know how it's done in here. I know that Anchor has examples. Tests, escrow. So there's a find program address where you basically put in the seeds and your program ID, and then it gets you a program address, and that already does the thing with if it's on the curve that it adds another bump seed to get one that is off the curve. I think the other thing is create program address, but that will fail if the first one is not, if the first one is on the curve and there is a private key for it. So find will iterate the bump seed and then also return the bump seed. So essentially I want to do this. Our Treasury PDA seed, we can just say our Treasury PDA seed is, I don't know, treasure. And then with our program ID, we can get the PDA and bump seed. And then we write that out, bump PDA with bump. Let's see if we can call that. For that, we need to deploy our program. We build it again. Oh no, we can't. I named this bump seed, of course. Oh, and that's not how you can concatenate strings. How do you concatenate strings? So that's number 1, and that's number 2. PDA bump seed. That's how we do it. This is how we do it, PDA. Well, some warnings, but who cares about warnings, right? Nobody cares about warnings. Doesn't matter. Okay, do we do that on DevNet or do we do that on local? Local would be faster. We're gonna do it on DevNet, I decided. Let's see what happens if I just type anchor deploy. I'm still in the way here, right? This is also not a good position for my face. Should I do the good old move away trick and then look down? Yes, that's the third position for my face this video. Great. That doesn't look good. Error, deploying failed. Custom program error 0x1. 0x1 was what kind of error? Insufficient Lamperts? It definitely took some of my sol. So the account that it uses is definitely the right one. Maybe I just didn't have enough. See, that's why you could work on local. There you can just airdrop yourself 1,000. DevNet seems to be somewhat stable, so just gonna try that again. 8 should be enough, I guess. It's looking better. There we go. Yeah, 2.2. So we've deployed this program on DevNet. Let's test it. So initialize is not here anymore, but we can print funds. Anchor test. Yeah, warnings, we can ignore that. Oh man, oh you did, wait. How was that? Skip deploy. There we go. Can print, failed. Fallback functions are not supported. Apparently I'm calling a function that doesn't exist. Oh, could it be that here you want it to be called like this and then you automatically translate it to that? I wouldn't know what else. QQQ2. Okay, we deployed it. And there you go. That really was the Well, first of all, I'm proud of myself for finding a solution to this that quickly. And you know, I'm getting better at this. I'm getting good at this. And I like it. There we go. Okay, but it's stupid. And yet I'm happy that I found the solution. Anyway, so that's my transaction. And now in the Explorer on DevNet, we can see what we did. And there it said found PDA with bump 254. There you go. That's what I was telling you earlier. We start with 255. So apparently on 255 it was on the curve, and then it used the bump 254, and that is not on the curve, resulting in this address. But that's cool. And sending stuff there is easy, right? If I want to fund the Treasury, I can be just like Solana transfer to this address, I don't know, 4.2 sol. We need to allow an unfunded recipient since there is no sol there yet. But then we can easily do that. So we don't need the program to go through the deposit. The deposit is easy. The withdrawal is hard. Because if we now want to get that out from there, that's not so easy anymore. Because let's look at this. It's now owned by the system program because I sent sol there. So the system program claimed that address. And we have the 4.2 sol. But nobody holds the private key to this address. There is no private key to this address. So in order to get the sol out of here, I need to have the program call the system program. So my program needs to call the system program and provide the seeds as a signer. And we will do that with our withdrawal function. So to withdraw, let's see if I can just do this. Then I need to import the system program system instruction, of course. System program invoked signed and system instruction, such that we can use it here, this and this. We do the same fun as before again. We get our PDA and bump seed and we transfer from the PDA to, where do we transfer to? Let's put in a receiver here. And Lampert's U64. So we say to whom and how many. And we need to provide account infos here. It's complicated again because I don't know how from my PDA I can get to the account info. Don't know if I need that, but let's put it here anyway. Then we need the system program, the destination, and our treasury. You know what? I'll leave that out for now. Because again, I have no idea how Anchor works. I'll just operate it as a normal account. The treasury, the destination, and the system program. And we sign it. That's the signer, the last thing here. So we put in our seed, our bump seed. With the seed and the bump seed, we should be able to get this transaction through. So let's see. I'm going to use this as my address. 1, 1, 2, 3, 1, 2, 3, 1, 2, 3. Receiver. Lampert's. First it needs to compile. Initialize. Oh, context accounts. It even says that here. Okay, it's getting better. Mismatch types. Count info and got pointer. Okay, then we don't need that here. Okay. Again, I have no idea what I'm doing, but we'll get there. Almost. See, I'm not a developer, and I'm not a Rust developer, and I'm not an Anchor developer, and I'm not a Solana developer at all. So this is confusing me. System program. How does that look now? Not good. Yeah, that's just a test that failed. Oh, that's good. That's good. Actually, that's good. Wrong input type for account system program. Then true story. Let's get the program ID. What is that? A public key. Perfect. Until it works, goddammit. We have half an hour until I need to leave. There we go. Whoa. I am surprised that this went through. Let's see what it actually did. Let's check this out. Okay. Nice. Wow. I am amazed that I actually made this work. I did not think this would happen, but hey, you see, from this address, our treasury account, we were able to get out 1 sol and put it onto our balance. Nice. So for our program call, that's the withdrawal, there's an inner instruction that it did. It called the system program. via cross-program invocation. And there it transferred one sol with the system program from here to here. A fucking amazing instruction withdraw. Now, obviously, we didn't do any checks like who is allowed to withdraw and that sort of stuff. But who needs that, right? Nobody needs that. Anybody who wants to call withdraw gets to call withdraw by putting in their address. Wow, that was actually easier than I thought. I thought I would not manage to do this. Yeah, I just defined my receiver here. I defined how much I want to receive. And that's the Treasury, we still hard coded in there. We can also do better and at least derive this as well, just so you see how we would do that in front end. I'm not sure, actually, it's in pubkey, okay. So, pubkey, find program address, and then here we need to define the seeds and the program ID from our program, and then we get the pubkey and the bump seed back. So we could say we want the same seed as here, so this thing. How would that work? Buffer from UTF, yeah, something like that. This, then I would put my seed here. What else does this need? So it's an array of buffers or integers. Then the program ID as a pubkey. Okay, so that's my program ID. And my program ID is this thing. And then we could check that what we get back from here, so that's our Treasury PDA and Treasury bump. We could assert that this is actually this, so let's print it out. Let's see if that would also work. That we don't need to know the address already, but we can calculate it by knowing the seed phrase. We can't sign it because we are not the program, so we can't sign a transaction. But we can calculate the PDA and we can send stuff there, or we can provide it as an account. Undefined. Okay, so that didn't work. Oh wait, I of course I need to await. Sorry, that's my bad. I of course need to await this thing. Maybe I need to write it like this. There we go. That's what I want to see. Yes. So here we have the address with that bump. So also in front end with anchor, we can just call find program address, put in the seeds that we want, like just a string, and the program ID. And as we had it here with the seed and the program ID, it will then find a pubkey that is not on the curve and give us the bump back, such that with all those things, we could now anchor create program address. So this is like find program address, but you need to provide the bump as well. Otherwise this will fail. So let's just to test out this as well for the fun of it. Let's put in the same arguments, and what we get back is just the public key. So failed PDA. If I put the bump, the Treasury bump here as well, that's how we do it. And then we have the, let's see this. All right, the transactions are failing now because we don't have enough SOL anymore on that account, but that doesn't matter. We're more interested in this thing. So that's what we get with the find. That's what we get just by create program address. And this thing apparently lies on the curve. And therefore we cannot use it as an actual PDA. But if we use it with the correct bump, then we again get this address. So yeah, create program address just uses the bump provided. Or maybe I got that wrong. Let's check once again if I used the initial bump here, because now we really used it without any bump. Maybe if we use it with the initial bump, it will fail, or will it always give us an address? I don't know. Inverted seeds. Address must fall on the curve. There you go. Okay, so then it will fail if we actually provide that bump as well. So in this case, our address now fell on the curve because we started with the 255 bump, and then the function will just fail and it will not return anything. It will throw an error, this create program address. Whereas the find program address, if that happens, it will just decrease the bump and try with the next bump. So that's why we want to use this find program address and then store the bump to then later just be able to call it with the create and put the bump in, or always call this, or even remember the addresses and whatnot. Anyhow, that's a lot of theory here as well for you in today's video with all that stuff. Well, I do hope that you learned something today about program derived addresses and what they're used for. Might have been a bit complicated, I admit. Might not have explained it too well, but the concept of PDAs is so important that I wanted to at least get started teaching you about it. I admit I could have done a better job in structuring this today, but we will keep working with PDAs in the next videos when I will create a Discord verification program. There I will definitely use PDAs. For every person who wants to verify, I will create a PDA for them. So it's good that at least we have a basic idea of what a PDA is, such that from now on we can start working with them. And they're super cool. You saw the program could sign something just by providing the seed. This is so cool. Now our program can actually hold tokens or sol and send and sign to send it out. And so cool. Yeah. I mean, I learned something today. For the most part, I still don't know what I'm doing. I'm just trying stuff out until it works. That's my style of programming. So maybe not the most secure kind, but we're still learning. And we will get there at some point, I hope. So I hope that you learned something today. If you like this video, leave me a like. You can subscribe to this channel to receive more Solana tutorials in the future. Also in the past, you can check out my other videos that I made. And I will see you in the next tutorial. Until then, bye-bye. Right on time. We finished right on time.